Hello students and welcome to a how-to video. Today we're going to be talking about half-life problems. We're going to be solving two problems together. This first one is relatively simple and the second one's a little more complicated. We'll walk through both of them and help you understand how to solve these half-life problems. And understand too that there is an equation for these problems, but the problems we'll be giving in class will be mostly based off of a time and amount t-chart. Okay. So in this first problem, plutonium-243 has a half-life of 5 hours. So that means in 5 hours, half of this isotope of 243 will decay into something else. What is the mass of plutonium-243 in a 56-gram sample of the isotope after 25 hours? So it's going to go through a series of half-lives, and we want to know how much is left at the end. So when we do set this up, we're going to have a t-chart of a time and amount. Clear. Okay, so we have a t-chart of a time and the amount. So in the beginning, okay, we have 56 grams, okay, and our time is 0 because that's what we're starting at. We haven't lost any time yet. It's our initial amount. Let me zoom in a little bit there for you, okay? All right, now it's going to half-life is 5 hours, and we're going to get to 25 hours. So what I like to do sometimes is to go through the time first, or if it gives you the amount, go through the amount first. But I'm going to do the half-life for this first. So if we look here, it's every 5 hours. So at 0, and then at 5 hours, 10 hours, 15 hours, 20 hours, and then 25 hours. And these are and it's good to specify as well because a lot of these problems will be either in seconds, they could be in minutes, they could be hours, they could be days, years, centuries. Like it's good to specify what reference we're using. So it's up to 25 hours. Okay. Now we're going to pull out our calculator and we'll just do it together. So what we'll do is we'll divide 56 by 2 and then divide by 2 again, divide by 2 again to show that half-life has occurred. I can scoot that over a little bit. So we have 56 divided by 2, and that is equal to 28. Okay, and half of 28 is 14. And then half of 14 is 7. And then half of 7 is 3.5. And then half of 3.5 is, I believe, 1.75 grams. Okay. So sometimes you can just do the math because it's an easy multiple. You can just divide. But the idea is every 5 hours, it loses half of itself. So in the first 5 hours, you now have 50% of what you started with, and that's 28 grams. And then you have 10. After 2 half-lives, you have a quarter of what you originally started with, okay? And it continues down. But the total mass of plutonium-243 after about just a little over 1 day is about 1.75 grams, okay? All right, let's solve this next problem. It's a little more complicated. Suppose an archaeologist extracts 20 grams of carbon from an axe handle and finds that carbon to be 1/4 as radioactive as a 20 grams of carbon extracted from a freshly cut tree branch. The half-life of carbon-14 is 5,713 years. About how old is the axe handle? So once again, we're going to set up our table. We have our time and our amount. Okay. And what we're starting with is 20 grams. So we're just assuming that we have 20 grams of this carbon in this ancient axe handle at the beginning when it was first cut down. So we have 20 grams, okay? And it's going to be starting at 0, okay? So what we're comparing is a cut tree branch today versus this axe handle, which was made out of a tree branch. We don't know how many years ago, but we're going to have to piece it together. And it says the carbon in the axe handle is 1/4 as radioactive as what we have today. So you're assuming that this has undergone 2 radioactive half-lives, okay? Because it went through a half and then now it's a quarter of the amount. So we have 20 grams, we're going to have 10 grams, and then 5 grams, okay? This original axe handle started out, we're assuming, with 20 grams or this a specific amount related to 20 grams of carbon from that handle. and we notice that it has a quarter of the amount. So it's gone through 2 half-lives. But what do we know about the half-life of carbon-14? It's 5,713 years. So 5,713 years is its first half-life. And if we were to half-life it again, 5,713 times 2 is going to be 11,426. Okay, so from this problem, okay, we can determine that because there's a quarter of the amount of carbon in the axe handle than there should be, okay, there's only a quarter of that amount of that radioactive isotope, we can assume that it had 2 half-lives, and that axe handle is about 11,000 years old. Okay, this problem is pretty cut and dry. It's pretty straight, kind of simple. When you're working with these carbon dating problems, they can be pretty challenging because it doesn't line up perfectly like this. Okay, we're going to have a lot of other steps that are involved, but in these problems, these are probably going to be your kind of more challenging problems as far as working backwards through this chart. A lot of times when you see problems, what you need to do is write down all the given information and then go back and try to get to the part of the problem that you're trying to solve. In this problem, we were trying to solve this, how much time there was. It was given to us was this information, and then we used this information to get this. So we usually have to just work our way through the problem and get creative about how we want to set up our table. Okay, so you got to think through these problems. While these ones up here are pretty straightforward. Okay, all right. Thanks for watching. Until next time.